Okay, so somebody's asking to look at the problem 9.030 for assignment 10. So let's just look at it. So basically, what is this? This is the sketch for the Brayton cycle. Okay, so basically here we have the figure of a Brayton cycle, which is the cycle that is used for what? Like for aerospace to the engine of the aircraft, no? Okay, this is a compressor, you compress the air. At the back, the turbine is what generates powers, but also is what drives the compressor. And then here you're gonna have a heat exchanger where you put the fuel and so on, which is gonna get burned, and then you need to cool it as well. So this is basically what we have. And it looks like they give you the value. So it looks like we don't have to go to the table. So an ideal air standard Brayton cycle operated at a steady state produces 10 megawatts. So what is that? This is the power over here, okay? Why is it people? Okay, so I guess I admit everybody. All right, so like I was saying, we're doing this problem out of the assignment 10. It's a Brayton cycle. It's for an ideal, it's for air, so an ideal substance. It gives us the power. Operating data at principal states in the cycles are given in the table below. Okay, so they give us the data, which is awesome. They ask us to find the mass flow rates of the air in kilograms per second, the rate of the heat transfer in kilowatts to the working fluid passing through the heat exchanger. So I guess is the rate of transfer in kilowatt to the working fluid passing through the heat exchanger. So I don't know if they want this one or this one. I don't know which one they want. The percentage of thermal efficiency. Oh, the top one. The top one. Okay, we'll figure it out. Okay. Anyway, let's do the figure and we take it from there. So if I do a quick figure, what we get is what? So 930, volume 930. So we have a heat exchanger over here. In here we have a compressor. Which is driven by a turbine. Okay, it looks like that's kind of the figure they give us. Q in, and then they kind of do another one here for the cold reservoir, but let's see what will happen here. All right, looks like they give us the power, which is generated by this, to be 10 megawatts. And let's see where were the points here. Okay, so 1, 2, 3, 4. Okay. So now this is 1, 2, 3, and 4. Okay, so basically, over here we could say what? Like for steady state implies what? That there is conservation of mass, which would basically indicate what? That M 1, 2 equal to M, 2, 3 equal to M, 3, 4 equal to M, 4, 1. And let's just call this one the mass flow equal to M, no? Yeah? Basically, the amount of mass coming inside the system is equal to the amount of mass coming up, no? If it goes in here, it comes in goes out. For this one comes in and goes out and so on. So we just say, we just have M. So we need to find the mass flow. So the compressor is going to require power, no? But we don't know how much. What is the component that looks like we know what's happening? It's on the turbine, okay? So let's say here, considering the turbine, as our control volume. And what else do we know? This is given an amount of power of 10 megawatts. And this is between 3 and 4. So if we apply the first principle of thermodynamics to this control volume, what do we have? Q dot minus power plus what? Plus M dot H3, now that is going in, will be equal to M dot H4. Is it any heat exchange of this component? So this is 0. And here basically we're gonna get that M dot H3 minus H4 equal to the power, or we could say that the mass flow will be equal to the power divided by H3 minus H4. I mean, you see that it's always the same procedure in all the problems, no? Not like. So basically now we need to do the numerical application. We're gonna have M dot is equal to power divided H3 minus H4. So let's see, what do we got? What do we have here is, I think that was 10 megawatts. So it should be 10 to the 6 watts per second. What is a watt? It's a joules per second, no? Okay. And now H3 minus H4. So I think the H values were given. So let's see what we have. H3 is 2002 minus 989.6. And oh, be careful here with the units, because what are the units for this? Okay, kilojoules per kilogram. So maybe we need to be careful here. Kilojoules per kilogram. So maybe here, what would be more convenient to do? Keep kilowatts and put here to the 3, no? So go ahead and calculate this, but if we didn't do anything wrong, what should we get? Is it 14.82?
I did this in the solution. He did it differently. They have worked out over H3 minus H4 minus.
Okay, guys. So like I was saying outside the recording, I did a mistake here because I assume that the 10,000 megawatts of power were generated only by the turbine, but it's actually generated by the whole cycle, okay? So which means that it's not 10 megawatts out of this one, because this is probably gonna generate more than 10 megawatts, but some of it is gonna be run by the compressor, okay? So what we can do now, we need to take another control volume and do another control volume for the compressor, okay? So let's go back here and see if we can use these calculations. So disregard maybe this here over here, this page. And let's just call this one here on the first equation, instead of just power, call it power sub T for turbine. And this will be power sub T for turbine, okay? And probably we're not gonna need this form. We'll see what we can do. Maybe we can use it. Okay. Now we do exactly the same thing, but we're gonna take as our control volume the compressor, okay? So we follow the same procedure. We say considering the compressor as our control volume. And what do we know about the compressor? That is going to require power to run. Maybe go to this figure here and put, this is WT, and scratch the 10,000 from the previous figure, okay? Scratch the 10,000, because this is what we did wrong. All right, so now from this figure, we can write the first principle of thermodynamics, which will be what? Q minus power compressor plus M dot. This is between 1 and 2. So plus M dot H1 equal to M dot H2. So from here, there is no heat transfer loss or gain. We can get that the power of the compressor used by the compressor is M dot H1 minus M2. Okay, so let me say, okay. So summary of what's happening so far. So far, what do we know? We know that the power generated by the turbine is M dot H3 minus H4, and that the work used by the compressor is M dot H1 minus H2, okay? So what do we know? That the total power is equal to what? Is the power generated. So this value should be positive, the generated, plus, I'm pretty sure this value will be negative. Check, is H2 higher than H1 on the table?
Yes.
H1, so H2 higher than H1, so this value should be negative, no? Because by the sign convention is what? The power done by the system is positive, the work done on the system is negative, okay? So basically what do we know? This is the mistake I did before, I'll reiterate, it was my fault. This is over here our 10 megawatts, no? Okay, so we can rewrite as saying that the total power would be equal to M dot H3 minus H4 plus M dot H1 minus H2, which will give us at the end that M dot will be equal to what? Will be equal to the power divided by H3 minus H4 plus H1 minus H2. So now if we do the numerical application, we should get that m dot equal to 10 to the 3 kilowatts divided by, so let's see what H3, H4. So 2002 minus 889.6 plus H1 300 minus 637.8, and this should be kilojoules per kilogram. So this time, hopefully we did not do any mistake, or I do not do any mistake. This should give you, what was the 14 point something kilograms per second, but can somebody do the calculation, please? 14.82. Okay. Okay, so you saw my mistake, again, I reiterate, is because I did the wrong free body diagram, no? So really on this figure, this is not 10 megawatts. So this is turbine compressor. So you see that if you do a wrong figure at the beginning, it's going to lead you to a wrong result, no? So let's see, the next thing we need to find is to find the rate of heat transfer in kilowatt to the working fluid passing through the heat exchangers. So I guess is this Q over here, okay? So again, what do we need to do? Control volume will be this, no? And we do, so basically what should that be? Probably would be H3 minus H2, no? So it will be pretty simple, okay, but let's do it. All right, so this time we take the heat exchangers as our control volume. So let's say considering heat exchanger as our control volume. You know, this is 2 and 3. What do we have? Q dot minus power plus M dot H2 equal to M dot H3. In this case, what we don't have is any work. So this is gonna give us that Q in is equal to M dot H3 minus H2. So if we do our numerical application, we're gonna have Q in will be equal to the 14.82 kilogram seconds times H3 is 2002 minus H2 should be 637.8, I'm getting this from the previous calculation, okay? Just looking at these values here. And this is in kilojoules per kilogram. So basically what you see, you're gonna get kilojoules per second, which is what? Watt, no? And the kilograms will cancel out. So whatever it is, this is the result, will be in kilowatts. Do the calculation, but at the same time, we can go and check over here, I'm guessing. So part B, 20, 22.0. Is that what we get doing the calculation or close? What do you get?
20,217.
So 20. Okay, so let's say we take this value 220, 2220. Okay. Whatever it is, okay, I don't have a calculator. And part C, what is part C? The percent thermal efficiency, okay? So again, you can go to the Brayton cycle and find out what is the efficiency, but otherwise, what do you know? Brayton cycle is a power cycle, no? Okay. So let's see what we need to find in order to do the power cycle. So Brayton cycle is a power cycle. So if you had to do a figure very quick representing the power cycle, what you do here, you see this is the Brayton cycle that operates between a hot, this is your Q in. This is going to generate power. And this is going to a cold, no? So I guess we're gonna have to do another problem to find Q out. Looks like, no? So what is the efficiency? Is whatever you get out divided by whatever you put in, no? So what are we getting out over here? Power. What are we putting in? Q in. Sorry, I did hear a mistake. What are we putting here?
It's just Q out in.
So it should be, so what we're putting is Q in only. Yeah?
Yeah.
Okay. I was thinking because what is the above? I was thinking ahead. What is the total power we can get ideally? Would be Q in minus Q out divided by Q in. So that gives us that the efficiency, I mean, we could use the first expression, but basically would be equal to what? 1 minus Q out over Q in. So what does that mean? That we need to find Q out. How do we find Q out? The same way we did for this one, no? Yeah, okay. So let's do it. So let me write over here, considering the other heat exchanger. This one is operating between 0.4 and 1. Is this one over here? We need to find Q out, okay? This one over here. We have Q out. This is our control volume. we write down the first principle of thermodynamics, we get Q dot minus power plus M dot H4 equal to M dot H1. There is no power used or created over here. So this is gonna give us that Q out is equal to M dot H1 minus H4. So we do the numerical application. Q out is 14.82 times 300 minus 989.6. So what do you get? What do you get if you do this?
Negative 10,220.
220?
Yeah.
Okay, so now the efficiency. We know that it was equal to 1 minus Q out over Q in. So this is going to give us 1 minus. So here, be careful. We don't need to put the negative value, no? Just the magnitude. So be careful with that. 10,220 divided by the Q in, which is 20,220. Whatever that is, probably about what, 50%, something like that?
49.
29?
49.
Oh, 49. Okay. I was like 29, something wrong with the calculator because this is basically 1/2, no? So let's see if that is what they get. I mean, you got the numbers, not me. So I just did the procedure. So again, on this one, so Q in, part C, 49.45.
49.46.
Okay. I mean, the procedure is here, no? The calculations. Don't do too many round off and just give whatever is the result because the software is picky with the rounded off. Okay, so next we're going to look at the 9.037 out of the last assignment. So 9.037, which I guess is 9.37. And they say there is a air enters the compressor of an air standard Brayton cycle with a volumetric flow rate of 60 cubic meters per second at 0.8 bars, 280 Kelvin. The compressor pressure ratio is 20 and the maximum cycle temperature is 1800. For the compressor, the isentropic efficiency is 92%. And for the turbine, the isentropic efficiency is 95%. Okay, determine the net power developed in kilowatts, the rate of heat addition to the combustor, the percentage of thermal efficiency of the cycle. Okay, so over here, okay, so first thing I will do the figure for the Brayton cycle that we just did, and then we'll have to do more figures, no? But let's say here. So I will do Brayton cycle. Again, we know that you need a compressor. you need, this is a heat exchanger, but this should be like a combustion chamber. Now we're gonna come here to a turbine. And this will be now another compression here. So compressor, turbine. And I mean, hopefully we use the same notation. 1, 2, 3, 4. This is Q in. This is Q out. Okay, so what do we know? So we know it's air that enters the compressor at an standard Brayton cycle with a volumetric flow rate of 60 cubic meters per second. So volumetric flow rate is what? Is AV 1 equal to 60. Yeah, I know, but I need to look also at the problem. So volumetric flow rate is AV. This is the velocity. What else do we know? At P1 equal 0.8 bars, T1 equal to 280 Kelvin. The compressor pressure ratio is 20. So what does that mean? P2 over P1 is 20. So once you put inside here a pressure of, let's say, 1, you're gonna get 20 at the outback, no? At the exit. And what else do we know about the problem? And the maximum cycle temperature is 1800 Kelvin. For the compressor, the isentropic efficiency is, for the compressor, okay? And the efficiency of compressor is 92%. And of the turbine is 95%. Okay, so let's see what we need to do. Determine the net power developed in kilowatts. Okay. So basically, we need to do the same thing as we did before, no? But this time with efficiencies. So maybe let's try it as you mentioned this time. Let's take as control volume both of these ones. Okay, but before that, we need to find what is the volumetric flow rate. Sorry, the mass flow. So in order to find the mass flow, I think we need to do that from the compressor. Okay, so in order to find the mass flow, what is the definition of mass flow? Is density times AV, no? So we could say that M1 is equal to AV1, and this is equal to what? volumetric flow rate divided by specific volume. What is density? Mass over volume, no? What is specific volume? Volume divided by mass, no? Okay, so we have the mass flow, and probably they say it's a steady state. So, okay, I'm gonna put it here. I'm not gonna write it down, but for steady state, the mass flow will be conserved. So it's the same M everywhere. So from here we have M1 equal to M will be equal to the volumetric flow rate divided by V1, just writing the same thing. Now, since we use air, we could use the ideal gas relation, which is what? PV, now you're gonna have to help me. D1 will be equal to what? R bar or no R bar in our class notation? R bar, okay. Or we could say here that D1 equal to R bar T1 divided by P1. Okay, so at the end we have that the mass flow will be equal to A D1 divided by R T1 divided by P1. Okay, so over here, I let you do the numerical calculation on the numerical application on your own. We know AV1 is equal to what? 60 cubic meters per second. T1 is 280 Kelvin. This is 0.8 bars, so probably you need to change the bars to kilopascals, no? Okay, and now what is R bar? R bar will be the, for us, R over the molecular mass. So the top is what? Is it 8.314? 8.314. And I think this is on the book for air. I think it's 28.97, if I remember properly, from table A1, no? So I'll let you do the numerical application. I'm not going to write it down. But again, we should end up with, I think, kilograms per second. Oh, so they don't give us the middle step, so you need to give it to me no matter what. Please don't do too much of a round off. So in this case, you get for M 59.73 kilograms per second. All right, so now, because we have isentropic efficiencies, and we don't have all these values for P2, so we have P1. All right, so, okay. So this should be page 5. Yeah. All right. Okay, so let's follow the problem here. Okay, let's do first the general equation and then we see what we need exactly, okay? If I can zoom out a little bit, no. So what we're gonna do next to change as before is that we know that the turbine generates power and we know that the compressor requires power, no? So it's the same as before, but let's try something different. This time we're gonna take as our control volume the compressor and the turbine. So for the below control volume, so let's see what we have over here. We have here, there is a, so this is 3, 2, 1, and 4. And here we have power compressor, power turbine, no? Okay. So for this control volume, let's apply the first principle of thermodynamics. So we'll have Q dot, and now we need to be careful here, minus be careful here now with the sign. So I guess we need to do work. Oh, it's good because we can do work turbine minus work cycle. Oh, no, let's use the, yeah, so this one is coming in, this one is coming out. They should come positive. I don't remember what will happen. I mean, what should be the right order here?
It's turbine minus compressor.
Yeah, this is really the work of the cycle. Really is what we're looking for. So, but okay. Hopefully we get a positive value. That's my dot over here. And now this should be equal to what? What is coming in? Plus m dot h1 is coming in into the system. And what else is coming in? H3. And what is leaving is m dot h2 plus m dot h4. So in this one, there is no heat. And we know this is actually the work of the cycle. So we could solve here for the total power of the cycle. Should be equal to what? M dot of H1 plus H3 minus H2 plus H4. Okay. So we know what is the mass flow. So we need to find H1, H2, H3, H4. Okay. So H1 is easy to find because what do we know at 1? We know P1 is equal to 0.8 bars and T1 is equal to 200 Kelvin. So we know two things. Probably we can go to one of the tables. Okay. Okay, so we go to table 822. We know the temperature is 280. So at 280, we found that the enthalpy is 280.13. So we get H1 equal to 280.13 kilojoules per kilowatt. Okay, now in order to find what is the enthalpy at 2, we know what is the difference in pressure, but that's all we know. Okay, so we need to find another property. So let me pause for a second and let's go to the class notes. Okay, so going back to the class note for an ideal gas relation, for ideal gases, isentropic quantities, we derive the relation P2 over P1. Let me write over here relations. And we have P2 over P1 equal PR2 over PR1. So how can we use that? So that means that now we can come over here and in order to find PR2 will be equal to what? PR1 times P2 over P1, correct? What is P2 over P1? 20. So we need to find PR1. So PR1, from where are we going to get it? We're going to get it from the first state over here. So from the table 822, we should get here PR1. And that should be, so at 280, should be 10.37.
Oh, that's a temperature spike.
Oh, sorry. So you see, good to check. So it's 280, then is 1.0899. Thank you for that. 1.0889. So we do the calculation for PR2. So you do 1.0889 times 20. So let's do it right here. 1.0889 times 20. What do you get for PR2? So 20 point something, but what do you get?
21.778.
21.778?
Yes, sir.
Okay, so let me go back over here. Resume. So like I was saying, we're not going to waste a lot of time interpolating, okay? But basically we need to get the 21.778. So we see it's going to be between 650, between this value here and this value here, okay? And since we're lucky enough to have on the solution the same values, they're not different, I'm just going to give you directly the values of interpolation, okay, from the solution. So let's say here, I'm going to go now over here. I mean, I will take these values now from here. I will say interpolating from table A22. Really, I don't know if we need that much T2S, but I know we're going to need H2S. They give us that in the interpolation, so we might need it later. Let's take it now. So what would that be here? So for 21.778, T2S is 649, so it's very close to 650, as we were saying, 649.3 Kelvin. And H2S is 659.13 kilojoules per kilogram. Okay, so now, let's go back. All right, we have this. So now, what is the efficiency? We know the compressor has an efficiency of 92%, okay? What does that mean? Again, we could go and rederive the expression for the efficiency of the compressor, but we're not gonna do it, all right? So the efficiency of the compressor, we're gonna go back to the notes. Let's see if we can find it in here. Maybe it's not this one. Isentropic aircraft modeling. So this is, we were talking about the Brayton cycle. Brayton cycle efficiency. We might need this one later. Back work ratio. Probably before that, we did the efficiency of the compressor. So going back to the note, we found that the efficiency from this figure of the compressor is equal to H2 minus H1, H2S minus H1. So we know so basically we need to find H2. We know H1, we know H2S, no? So this will give us what? So this is gonna give us that H2 is equal to H1 plus the efficiency of the compressor times H2S minus H1. Okay, so since we don't have much time, let me do some cheating again. We go to the solutions, okay? So H2, I guess they have the same equation. You see, let's see, H2, they have H1 plus H2S. Ooh, is it divided or multiplied? Did I do something wrong here? What do they divide by the efficiency? Should not be divided, no?